it's time to apply what we've learned about equilibrium to acids and bases. So acids and bases we're probably somewhat familiar with. So let's go over some of the properties that we do know of for acids and bases. Acids, let's see, what do we know about acids? They usually add H plus ion to solution. We normally think of them as increasing the hydrogen ion concentration. And bases usually add OH minus ion to solution. We also know that, there we go. We also know that acids tend to taste sour, although we usually don't encourage tasting things in the lab. So things like citrus fruits, lemons, limes, taste very sour. The sour taste that you experience in warheads, they basically take powdered citric acid and put it over the outside of the candy coatings. That's where you get that really, really sour taste. Bases usually taste very bitter. If you've ever had baking chocolate, that's a very bitter taste. If you've had your mouth washed out with soap, that's a very bitter taste. Acids will neutralize bases. And bases, of course, will neutralize acids. Acids tend to react or corrode metals. And bases tend to be very corrosive to skin and tissue. In terms of indicators, we have phenolphthalein. Oops. Where the base is going to be that nice pink color, and an acid it's colorless. So it's kind of a common indicator, and we'll learn about others. The litmus is another indicator, litmus paper. In base it's blue. It's kind of easy, base and blue, to remember that. And in acid it's red. Okay. And the other thing that we'll learn about later on, probably one of the next video, is the pH. So in acids, the pH is less than 7, and in bases, the pH is greater than 7, so that scale. So this is some properties of acids and bases that'll get us started, and obviously we'll get into some more of the properties of these as we go along. The most basic definition of acids and bases is the Arrhenius definition. So the Arrhenius definition of an acid is a substance that, when dissolved in water, increases the concentration of hydrogen ion. So you can think of one of the common ones that we've used would be HCl. Right? Bases, on the other hand, are substances that, when dissolved in water, will increase the concentration of hydroxide ion. So you're looking at ionic substances, metal hydroxides, probably the alkali metals, because they're always soluble. So if we were to take sodium hydroxide and put it in the water, that would be a classic example of a base. Now, the next definition we have is called the Bronsted-Lowry definition. An acid in the Bronsted-Lowry definition is a proton donor. So this must have an acidic proton. Again, HCl works fine for this, as does HNO3, nitric acid. Organic acids are acetic acid, HC2, H3O2. All right, that first hydrogen is designated as being an acidic hydrogen. Bases, now, on the other hand, are going to be proton acceptors. So they're going to accept an H+. Now, to accept that H+, really what they need is a lone pair of electrons. When you dissolve the metal hydroxides in water, what you're really getting is that OH-. Remember, OH-, if we look at the dot structure for this, we're going to have this as a dot structure. You look around that oxygen, and there are 3 lone pairs around that oxygen that proton is able to basically attach to or bond to. So that would be what's called a coordinate covalent bond, where the hydrogen would bond onto that. So a base is a proton acceptor, something that will take a proton away from an acid. The term given to a substance that can do either is the term amphoteric, something that can both donate a proton and accept a proton. If you used hydrogen carbonate, would be a good example. So bicarbonate. Notice that bicarbonate has a hydrogen ion here that it could donate to become just the carbonate. It could also accept a proton to go back to carbonic acid. Right. So the carbonate ion is what we refer to as amphoteric, and it can either lose or donate a proton, or it could accept a proton. When acids dissolve in water, they ionize, right? They break apart into ions. So here's the what happens when hydrogen chloride gas is dissolved in water. You can see that the water is going to accept that proton, which in this case then makes water a base. So if we look at our situation here, here's our acid, and water is going to accept that proton, which makes it the base. Right? Now, what we produce in this reaction then is a substance that can then act as a base, which is the chloride ion. So the chloride ion could potentially gain a proton, which makes it a base. This is called the conjugate base of the HCl. So that's a conjugate acid-base pair. Likewise, the hydronium ion, the H3O+, is the conjugate acid of the base water. So we have conjugate acid-base pairs which differ from each other in just one proton. The acid being the one with the proton, the base being the one without or minus one proton. Here's a reaction between nitrous acid and water forming nitrite and the hydronium ion. And so you can see that the nitrous acid, the HNO2, is going to donate the proton to water, right, becoming the NO2 with a minus charge. So there's one combination of acid conjugate base pair. And then you have the other one, the water, gaining the proton and becoming the conjugate acid H3O+. So it's important for us to be able to identify these conjugate acid-base pairs. We also want to get a handle on the relative strength of different acids and bases. So here's a chart, and we'll be going over this and doing several problems and examples in class. But you can see that not all acids are the same strength, likewise with the bases. We do follow a pretty standard trend that the stronger the acid is, the weaker its conjugate base. So HCl is a very strong acid. Its conjugate base, Cl minus, is negligible, if any, kind of basic properties at all. It's not very likely to gain a proton at all. So that's our strong one. Our other halogens are also strong acids. So we can lump in with this HBr as well as HI. So those are also going to be strong acids. HF is not going to be a strong acid, and we'll talk more about that a little bit later as to why that is, but you can see where that falls on the chart here. It's more toward the higher end, but it's not completely strong acid. And now you go back down here and you can check out water. You know, water obviously is not a very strong acid, and the OH minus is a fairly strong base. And you can see the bases that are stronger than it would be the OH minus, the H minus, and CH3 minus. So those would be stronger bases than the OH minus. All right, in any acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. So, you know, in this case, you can see that for the hydrogen chloride, when that goes into water, it's going to go 100% to the hydronium ion and the chloride ion. The chloride ion is not going to be able to take that proton away from the hydronium ion, the H3O+. Water is a much stronger base than chloride, Cl minus, so the equilibrium law is far to the right. In other words, the K value is not measured, but it's very, very, very large. All right, finally, if we look at acetate, acetate is a stronger base than water. So in this case, the equilibrium is going to favor the left side. So again, you have acetate here is a stronger base than water here, which means that it's more likely to gain the proton away from the hydronium ion to form the acetic acid. So in this case, the equilibrium in the way that the direction it's written is going to be much less than 1. All right, we'll continue on in the next section with what's called the autoionization of water.